Right. So it's a great pleasure for me to introduce Professor Andy Ruina. Professor Ruina is a John Carr Professor of Mechanical Engineering at Cornell, in the Sibley School of Mechanical and Aerospace Engineering. So he was born on the East Coast, I think, from Providence, and he did his studies at Brown, both from bachelor to Ph.D. And is a great expert in many aspects of mechanics, robotics. He started with solid mechanics. In particular, he was working on friction, and he has many great results, as I mentioned, from robotics to dynamics to biomechanics. And his lab has made constructed some of the most energy efficient working robots. And there is a lot of work, Professor Ruina, on theoretical applied aspects. He worked on collision problems with non-holomic constraints, and it's a great pleasure to have him here. And I think I would say enjoy your talk because it's going to be great. So thanks, Professor Ruina, for your time, and please go ahead.
Hi. Okay, so my talk today is control of bipeds, how to make a robot walk that uses little power and doesn't fall. Now, if you say, the key idea is to make a robot, I'm actually not that interested in robots in the end. So you can think of this as trying to understand people by trying to reinvent them. Sometimes people say, oh, look at the amazing things in animal design or human design or biological design. I don't think you have a right to say that until you've tried to solve the problem and have some appreciation for what the problems are. So, of course we can see, all right, human bodies are beautiful and the animal bodies are beautiful and there's all kinds of complexity. But unless you know what the problem is, say with walking or balance, you can't, you don't really have a right to say that. So that's why I think studying bipeds, robots, is a means to studying people and animals. So the first thing I'd like to say is, can you turn on your cameras? I'm always glancing down to look at people's faces to see whether they look puzzled or curious or whether they're laughing at my jokes or not laughing at my jokes. If you're in a quiet place, you can even unmute your microphone so you can shout out questions. I guess there are not going to be a lot of people here, so we can keep it pretty informal and just interrupt me anytime you want. And then I guess if we go late, I come back another day. Okay, so this problem of walking or balance is you could say it's a hard problem because the governing equations are nonlinear. The robot, the people are underactuated because there's more degrees of freedom than there are motors. Actually, if you look at a person, there's millions of motors, but they're not in the right places. The system is what's called a hybrid system, which is when you try to write equations of motion, they change in the middle of the process. For example, depending on whether 1 feet or 2 feet or 0 feet are on the ground or whether the leg is straight. We don't have great sensing. Some robots can have good sensing, but most robots actually have a sensing problem. Mechanically, you can think of this as non-holonomic. This is a technical word which most people don't know, but I have a whole lecture I can give on this topic. You can just ignore it. You can just say this is a big word people use to try to make it sound like they're doing some hard problem. There are many degrees of freedom. There's hysteresis and so on. So people think of this walking problem, like making a robot understanding it, is hard in these ways. And I actually don't think so. So I don't think this walking problem is particularly hard. Okay. So let me go on here. There's 6 of you who don't have your cameras on. If I was teaching a class, I would stop at this instant and make you turn on your cameras. But really, it's nicer for me if you turn on your camera. So I know everybody thinks, hey, I'm just watching, don't count me, but come on, just. for it. Kelsey, Nate, Jessica, Foster, Ben,
Someone is
Kathleen.
cheating. Someone is cheating.
Someone is cameras. Anyway, you'll make me happy if you turn on your camera. Okay, so the goal is make or understand the control system for a robot or an animal person, and you want it to function, which usually means, most importantly, you don't want it to fall down. You want it to move in good ways, which is not objective, but it's you want it to look nice or go the right place, and you want it to be relatively energy efficient. And like people or animals are efficient, so how do you do that? If you look at this, from an engineering point of view, and you just start with videos that are a little bit old, you get these videos, which probably you've seen. I guess I'm going to the internet here. So this was about 6-7 years ago, and these were like all the best robots, and they all failed. And you could take this as a sign that the state of the art in terms of understanding balance and so on was pathetic. In this competition, I think every single robot sort of fell down like this. And then you say, well, what's the problem? And actually, the problem in this case is, none of these robots actually walked that well. But the falling down part was not because of lack of understanding. It's because of lack of money, basically. That these are university projects, and a robot is a complicated thing with lots of parts. And I think every single one of the failures was like a short circuit, or a battery went bad, or there was a bug in the program, things like that. There were sort of things that were not debugged, things that universities aren't good at. And on the other hand, if you have lots of money and you can hire competent people, you can do. Let's see if this goes well. You can do impressive things. So this is now a few years old, but and they're better videos than this. But this is Boston Dynamics, and they spent tens of millions of dollars and had really good engineers, and they can do impressive things. Now you can criticize their robots, or I can, because they're not energy efficient, but at least they function. So it's like, in some sense, you can make robots that do some lifelike things, but they're not that good in some way. Let me show you some more recent ones. Here's a company called Agility Robots, and they're actually selling robots now, and their robots work okay. They're not very human-like, and they do use a bit of energy, but they're okay. And they, it takes millions of dollars to do that. Here's just another Boston Dynamics video. And I guess you could look at this and say, okay, the locomotion problem is solved, but these use so much energy, and also these tasks that take so much planning. They're kind of scripted. So we want to do that better than that in some way. And here's like a way of trying to measure how we want to do. Is you plot on the axis how energy effective something is, which is the reciprocal of something called cost of transport. The cost of transport is how much energy you use divided by what you get, and it's like the cost to benefit ratio, and the cost is like gallons of gas, but if you want to be specific about energy, it's like joules of energy, and the benefit is how much weight you move, how much distance, and weight times distance has units of energy. Then you take the reciprocal of that, so it's miles per gallon instead of gallons per mile. And in this dimensionless way of looking at things, people have a cost of transport, or reciprocal cost of transport, of about 0.25, or cost of transport of like 4 or 5. The best robot we've made at Cornell is a little better than people. These typical good robots that I've been showing you are way worse. On the other hand, if you have a measure of performance, which could be how fast it can move or how cool it looks or how much people go ah when they look at it, say humans are pretty good, and the new robots from Boston Dynamics or agility robots are not quite human-like, and the Cornell robots, which I'll show you, which we made, are not very good at all. So the idea is you want a really cool robot that either goes fast or looks like a human or balances really well, and you'd like a really energy effective robot. And right now, you can kind of get one or the other, and we'd like to get up here, and I'm going to tell you today about a way to get here. Okay, so I'm going to try and sell you now for the next half hour or so an idea for how to make a robot that walks in a very natural way and doesn't use a lot of energy. And this is, I'm going to try and sell this idea to you, and then at the very end, I'm going to tell you that it's a bad idea.
So I have
Okay,
a
so
a
where were
couple of
we?
questions
Oh yeah,
actually.
turn on your cameras. Okay, so then the next thing
Oops.
is how we're going to do that.
So,
So the idea, which just sounds crazy to start with, is you try to make a robot that can walk by itself without falling, and then use that to add, and then add control to it. So you say, if I want a machine to do something, I'm going to control it with motors and so on. Why don't I just first make a machine that does it already, and then I'll add controllers. So the thing is, what does that mean? Well, it means we got to make a machine that without any motors or controllers walks. So it sounds like a crazy idea, but then I'm going to sell you on that idea, and I'm going to sell it to you by a sequence of 3 sort of example cases. One is how bicycles work, one is how airplanes were developed, and one is walking toys. Okay, so we start out with bicycles. It turns out that here's a bicycle, and you ride a bicycle and balance. It turns out that most bicycles have this feature that they can balance themselves. Okay. If you disturb them sideways, they pop up, they balance themselves. Now, if you're interested in this bicycle thing, I can give a whole talk on bicycles. And I can talk a little bit more about it now if you want. But the key thing is that you have that when you say, how do you learn to ride a bicycle? Well, maybe it's easier to learn to ride a bicycle because bicycles already balance themselves. Just out of curiosity, those of you who have your cameras on, can you raise your hand if you knew this feature of bicycles already? So you already knew it. So how did you know that?
because I saw your video.
You're muted there, Alessandro.
I think I should be unmuted now. I think I saw your videos. That's why I
Muted,
know.
or maybe you're not muted. Maybe I'm muting you. Keep talking.
Because I've seen your videos.
Oh, I don't hear. Actually, this is a bad thing that I don't hear anything. We've lost my sound control. Let me
Yep.
just try to get my sound back.
Yeah.
I don't hear anything. I don't hear anything. I don't hear anything. Okay, we're gonna have to spend a minute with me getting my sound back.
Yeah.
Okay, try talking now. I still don't hear anything.
Can you hear me?
Now I hear you. Yeah, good. Okay.
Yes.
Good.
So my answer was that I've seen your videos.
Oh, you've seen my videos. Okay.
So then I
Okay.
know.
Okay.
I actually can get back. I had one question on the previous slide. The slide on the performance versus energy effectiveness, one over cost of transport.
Yes. Okay.
So
Yes.
maybe I can.
Good.
Maybe, I have 2 questions actually related to this. Is it true? Is it really that flat, the curve there?
Is this flat up here, you mean?
Right.
No, this is just a random curve.
Right.
So the generic, this is what's called a Pareto front, where you're trying to optimize 2 things.
Only the front, yeah.
And sort of the generic shape for a Pareto front is a circle or an ellipse. So just think of this as, there's always a trade-off. If you have some feature and then you want to make it more inefficient, you have to you have to give up something, right?
And
You
then the
made
curve,
something as good as you can in one dimension, then to make, and you say, no, I also want to do this, you've got to give up something on this side. So there's always a curve, and it tends to be sort of circular, sort of generically sort of
and then
circular.
the shape of the curve is actually task dependent, right? So you're gonna have some, depending on the task, you're gonna have a different curve, right?
No, it can, yes, right, and this curve in particular really has no meaning because I didn't give an
Yeah.
objective definition of this thing called performance.
Right.
I'm just trying to show there's a trade-off,
Yeah. Good.
and
Good.
obviously humans are more cool than any robots we've made, and the robots we made at Cornell are less cool than the robots people made other places. Okay, so here's this thing. So we start with bicycles like this, um, and let me just tell you a little bit about it. People knew that bicycles had this feature, 125 years ago, but we do not know actually whether when people first designed bicycles, they were doing this on purpose or not. Nonetheless, this feature of bicycles has survived for 120 years. It's not that every bicycle can do this, but lots of them can. Okay, so that's this idea. Okay, bicycles, they balance themselves. Maybe that makes it easier for us to ride the bicycles. Okay, let's go on to an example. The next example is airplanes. This is the Wright brothers airplane, and which is a glider, and this is the Wright brothers powered airplane. This photograph is said to be the most famous photograph of anything, anytime ever, according to the New York Times, like the most famous photograph, period. And this is the first time the Wright brothers flew an airplane. So here's what I want to try to convince you is that the Wright brothers did some very sensible thing, which is different from what other people did, which is instead of just trying to make a powered airplane, they said, let's make a glider first and make a glider work, and then we'll make an airplane. Okay, so I want to just tell you a little bit about the logic of that, and I'm going to explain the logic of that with me here and a paper airplane. So if we were in a bigger room, or if I was in a bigger room or something, I would demonstrate this paper airplane I would throw it, and if I throw it hard, it does funny things, but if I throw it just sort of gently, the airplane just glides down, like so. Okay, so the way the airplane works is there's gravity here pushing down, vertical gravity, and the plane goes on this gliding path like this. Now, what you can say is, okay, we've got this glider and we've got it working. If we've got a glider working, then this is kind of almost mathematical, what I'm going to say. The air doesn't have any natural direction to it. The only natural direction of this comes from gravity. So I could take this picture with this glider like this, and I can rotate the picture like this. And now I have a crooked gravity field and an airplane which goes on the level. So if I can make a glider that goes down, then I can make an airplane that flies straight. All I have to do is get a crooked gravity field. But obviously we don't have crooked gravity fields, but if you look at this force here, I can break it up into a vertical force and a horizontal force. And that you say force is a vector, that's what we teach in physics classes, force is a vector. What that means is the effect of one force added to another force is the effect of a combined force. So this force is equivalent to this plus this. This force, hey, this is the one we've got already, that's gravity. So if I could add to make crooked gravity, I just take my airplane, my glider, which was working fine like this, vertical force, rotate it so it's flying level with this crooked force, and then say, oh, I've got that gravity, that real gravity. I'll just add a sideways gravity, just some force in that direction through the center of mass. And if it's really a force in that direction through the center of mass, it's mechanically equivalent. So if this plane worked, this plane has to work with a motor in that direction. So when the Wright brothers mastered gliding, they knew they were going to succeed because they just had to add a horizontal force, and then this thing with a horizontal force and a normal vertical force is just like this one with a vertical force and a plane that's flying down. So they were completely confident that this was going to work. And then I think they wrote a letter. The sister says Tuesday we're going to have the first powered flight. And they did not because something broke. So there's always a systems engineering problem. So their understanding was good, but they got it to fly the next time after they fixed the airplane. This is what they got. So you can kind of know that if you can get a glider to work, you can get a powered airplane to work. Okay, so this is the actual history of flight, right? They started with a machine that could do the task without a motor, and then they added a motor and got a machine that did the task. That's the history of airplanes. Now the last example I'm going to give is walking toys, and toys have been around for a while. Here's the oldest patent we could find for a walking toy. That's 1888. It's this funny wire machine. I never got one to work, but in Delft they made one, and this was Martijn Wis, who started with making robots in my lab. He became a professor in Delft, and one of his students got this thing to work. So this has no motors and no controllers. It's walking downhill. You can't tell it's walking downhill. It's actually just two pieces of wire. There's one wire that goes up here, it wraps around here, it goes up to the head, comes out, and it goes to the right arm. The left leg comes up, wraps around here, goes down, becomes the body, becomes the right arm. If you look at it, the right arm and left leg is one piece of wire. The left arm and the right leg is one piece of wire. And this thing walks downhill. The famous walking thing is Slinky. But it's just more conceptual than it is like really walking, whereas this thing actually looks something like walking. It's got some of the geometry. If you haven't seen it, you should watch Slinky on a treadmill. Raise your hand if you want me to show it to you right now. 1 minute distraction. Okay, the vote is 3 people don't want it. Okay, we're not going to do it. So look it up. Well, we got 3. Okay, we got a majority. So let me show you this. You can just do a Google search on Slinky on treadmill. And this is, it's conceptual walking. It's not like really real walking. But you put a Slinky on a treadmill and it will go for a long time. So now this is always walking downhill, but it goes. And there's several videos of this. This was only discovered like about 10 years ago, as far as I know. This feature of Slinkies, that you could put them on a treadmill. Okay, then there's this toy here. This one is patented in 1938. This is one that maybe Michelle would be old enough to know about. It was popular in the 40s and 50s. And here's the patent description. And this is there are hundreds and thousands of these things around. You can buy them on eBay for between like $500 and $300, depending on their different body shapes and so on. But this is just walking downhill again with no motors and no hinges of any kind. Okay, so this is actually the starting point for a whole science of walking. This exact toy. Not this particular instance of it, but this exact design. So a guy named Tom McMahon, who was a professor at Harvard in biomechanics, he got this toy when he was a kid, and it inspired him. And then he got a student named Simon Mochen, and this is in the maybe early 80s, late 70s, to do a calculation. And the calculation that they did, now you got me again, is they assumed that they had a triple pendulum, and the triple pendulum is made up of a stance leg, the whole leg, and then the swing upper leg, the thigh, and then the swing calf. So you're thinking of walking as this 3-link pendulum, but they just looked at one step. So they launched the thing in one configuration, and then solved the differential equations of a pendulum until the next leg hit. So it's, see, I'm not used to doing this without being able to stand up and show it to you. But just imagine all you're seeing is a leg and another leg, and it's three links. This one leg goes from the hip to the ground, one is the thigh, and one is the calf, and they launch it just at the beginning of step, and it swings over, and it looks a lot like a person walking. So it was this triple pendulum, and this is before computers were so prevalent, and before lots of people were solving equations of motion and things like that. And that was inspired by this because it was, just mechanics. So it just showed that one step of one person is a lot like a triple pendulum if you go from the ground up to the hip and back down to the ground. So um, um, that was motivation for this idea that we're just sort of passive machines. So let me just give you a little more motivation. If you look at people when they walk and look at how active their muscles are when they walk, like with EMG measurement, you use a teeny fraction of your muscle capacity and your leg muscles when you walk compared to the strength of the muscles. So that it's very barely activated, your muscles, when you walk. You can look at all the little firings, and it's much less than, say, getting out of a chair or squatting or going upstairs. So then you think, oh, these things like these toys or these airplanes or these bicycles that don't have motors, they're passive, which means they don't have control, but they're passive, which means they don't have motors. So if you start out with the design that's not using motors, it's like inherently energy efficient. And then the last thing is, surely in our evolution, it was rewarding for us to be energy efficient. So, the story I tell is about my great-great-grandmother. Unfortunately, was not that efficient. Actually, my great-great-great-great-grandmother. And one day she was trying to go from one apple tree to another apple tree that was really far away, and she starved to death and died and didn't have any children. But my great-great-great-grandmother, she was energy efficient. She made it to the apple tree, and she had lots of kids who had kids, and that got to be me. So, that's the thing, is that if you're energy efficient, it gives you a survival advantage. So surely that's been part of biology for forever. So we want to be energy efficient. Passive things are kind of intrinsically energy efficient. People, we don't use much muscles, so maybe this is like really an idea for how it could work. So what happened is this guy named Tad McGeer, he saw that paper by Mochen and McMahon where they had this triple pendulum, and that triple pendulum only went from the beginning of a step to the end of a step. And he said, what happens when the foot hits the ground? Next foot. And well, it goes bang, hits the ground, heel strike, and it loses energy. So then he said, well, what happens if I supply some energy? Like I make it go downhill. Now, Tad McGeer was an aeronautical engineer, and he was thinking, oh, the Wright brothers made gliders before they made airplanes. So let's make a gliding robot. So here's kind of a picture. Remember, I was trying to describe this Mochen and McMahon calculation. Here's this is not a calculation, this is a robot, but you see this triple pendulum, that there's a one link, and you can see it taking a step. This is actually a video of a robot moving, but it's very close to their calculation. Then what McGeer did is he said, well, when it hits the step, it goes bang, it loses energy. Well, let's make up for that energy by putting it on a ramp so it goes downhill. He put that all in the computer, including the collision calculation, and then he found out that he could find periodic motions and that they could be stable according to the computer calculation, and he built this thing and it worked. So this was, I think, published this in 1990. This was basically this design is what got me into robotics. And so this here and here is a copy of McGeer's design in my lab. So this is Mike Coleman, who was a graduate student of mine, and this is in the late 1990s. We made this robot, and it looks, it's a very slight improvement of McGeer's design, and it walks just like McGeer. So this is McGeer's design, this is our copy. with very minor improvements. So you see it's higher over here than over here. So where's the energy come from? In going from here to here, it goes down a distance of 6 inches or so. The slope is 3 or 4 degrees, something like that. And there's no motors and no sensors. And, it's kind of remarkable, I still think, that this works, and it's so kind of evocative of human gait. And even though it's got no upper body and it's got this weird construction with 4 legs because it's really a 2-dimensional model, and this, the sagittal plane, the side view plane, and you have to give it 4 legs so it doesn't fall over sideways. It's pretty evocative of human gait, and therefore it got me and other people interested in this passive dynamic way of thinking about things. So, any questions about this robot?
I actually have one question.
You're mute, I think.
Can you hear
Or
me?
did I screw up my sound again, all over again? I do it or you do it?
Can you
You try to talk again?
can you hear me?
No,
Hello?
my sound system is up,
Hello?
sound.
Can you hear me?
Now, where's my sound settings? Up here, sharing, meeting controls, not mute. I want
Oh.
mute. Do you know where the settings are? You can't tell me because I can't hear you. Okay. View audio connection.
Hello?
Using computer for audio. That's fine. I want to use. I don't want to stop that. I don't want to mute all.
Everybody else can
Audio
hear, right?
speaker, microphone, and camera. I clicked on speaker, microphone, and camera, and it didn't do anything. Share application. Okay. Speaker, microphone, and camera.
You hear me? Yeah.
If this was Zoom, I would know where to find this.
So in the
I'm sharing Keynote. That's fine. You'd think something would pop up on my screen when I did that. It does pop up. It's just hidden. Speaker. Test my speaker. Here's something that's maybe more reliable. Oh, okay, I got it. I'm back. I'm back. I can hear you now. Okay.
Awesome.
Okay.
Yeah, so good. So no, my question was, so there is a bar there which connects 4 legs, right? So so how is that done? Like, is that is there some sort of freedom or somewhere? I don't understand how that is done.
Okay, so conceptually, so what you're supposed to look at when you see this is 2 legs. So you're only supposed to look at, say, the left leg and the right leg, and this leg has a thigh and a calf, and this leg has a thigh and a calf, and that's all we want. But we live in a 3-dimensional world, so if we want to take this 2-dimensional concept and put it in 3D, we have to keep it from falling over sideways. So what happens is this thigh is just connected mechanically all the way over to this thigh. So this is one piece of metal all the way over here. So the left and right thighs have to move together. And then this is the other leg. Sorry, this is not the left and right. This is the right thigh and its mirror image. And here's the left thigh and its mirror image. And they're one piece of metal like this. Then we have the 2 calves, which you could think of as independent. Sometimes we would put a piece of metal across here and sometimes not. This piece of metal actually is independent of this piece of metal, but it's just that somehow they entrain with each other because they both have the same They're both seeing the same thing. So the middle two legs, I can see there, these two calves are tied together. The outer ones are not, but they just entrain in the motion because the dynamics, some kind of dynamics that we did not study. Does that address your question?
Yeah, just in part. The other part is like that horizontal bar which connects the two central legs with the two external legs. Is it fixed to any of the legs?
This bar here.
Exactly.
Okay, it's only fixed to keep it from falling out. This is just a bearing. This is a bearing. So this is free to rotate on that bearing. This is all of them are free to rotate on the bearing. But
Right.
actually, it
Okay.
doesn't matter. I mean, that's equivalent to is fixed on the outer two and the inner two swing, or it's fixed on the inner one and the outer one swing, or it's not fixed on any of them and it just can't slide out. So this is just a hinge.
Okay. Good. So good. Good. So it's just an inch passes through the four
Yeah,
legs, but the legs can rotate.
yeah, yeah,
All the legs can rotate around that. Okay. Good.
yeah, yeah, yeah. Okay.
Good. Thank you.
Okay, so now we wanted to figure out sort of one interesting thing about this, which is this thing is stable, right? It doesn't fall down. And you'd say, well, why doesn't it fall down? And one way to think of why it doesn't fall down is that once per step, it visits this configuration where the legs are all spread out and it's stable, right? It can stand there stably. So maybe this thing inherits its dynamic stability from its static stability. So just freeze it like that. No, freeze it, try to freeze it just better. Bunk. It can stand like that. So, I can make if I have any kind of object and I put it on a flat surface, say I put my computer mouse on my iPad, and it's stable, right? There's no question it's not going to fall over. It's not going to fall over, right? Now, if I just jiggle this around and I do a complete detailed analysis of this, this is a dynamical system. It's like a boring dynamical system, but it's a dynamical system. And I could say, oh, look, the equations are really complicated and it still doesn't fall over. But it's not too convincing because obviously it's not falling over. It's like stable. And then I don't have to change it that much. If I take my computer speaker, the one that's not working for me, and I put it up here like this, and then it's got this feature about can I turn off that thing that makes my background disappear? Is that in my option list? Do you know? Let's see if I go to um, background um, preview. That's what I like. None. Is that the hidden background? Blur. I just want to do it just the way I am. Show me the way I am. Blur. Don't want to, none. There. Should be apply. Now, apply. It didn't work. Apply. Didn't work. None. Apply it. Um, well, okay, you can look at it like this. Do you see my screen right now? Do you see me? Okay, so now I'm using the video control didn't work, but so I have this thing balanced on this like so, and I can shake this around a little bit and it doesn't fall over, and it's dynamics and it doesn't fall. But just because it's dynamics and nonlinear dynamics doesn't mean it's not stable. Obviously stable because it's statically stable. Okay, so the question are these robots, these walking robots, and what do I mean by these walking robots? I mean this one by McGear or this toys. Are they stable because they've got big flat feet, or are they stable because they're like a bicycle and something about the motion makes them stable? So it's not quite a mathematical question because it's hard to know. But we thought, well, one way we could answer that question is, can we make a robot that's like a bicycle that when it's not moving, it doesn't balance? To just sort of show that the act of walking is a stabilizing thing all by itself. So Mike Coleman, my student, set out to make one of these passive robots that could walk, but it couldn't stand up. And there's an interesting story here, and that he did this on the computer for 2 years, calculating limit cycles and stability of limit cycles with this hybrid dynamics and all this stuff. And every design he put in the computer was either it could stand up or it couldn't stand up when it was walking. Then he switched to doing experiments, and he found one with these Tinker toys, and then 2 years later the computer agreed with it. So here's this thing. It's got these round feet, and the center of mass is above the center of circle of the curvature of these feet. So if you just put this down, it doesn't matter whether the legs are spread or not, it falls over. But it walks. And the computer agrees that it walks. So it shows in principle that this walking thing can be something like the bicycle thing. And the bicycle thing, you try to give credit for the bicycle because it's got spinning parts or so on. There's no spinning parts here. There's only about the motion makes it stable. Okay. So then we took that idea and we said, well, let's go back to the previous robot and really make it look three-dimensional. Now, we did not achieve with this robot what we achieved with this one, which is that it depends on dynamics to stand up. We made a robot which was essentially it was copying this design, but we only had the 2 legs instead of 4 legs. But we made the feet sort of chunky enough so that this one could stand up. But it looks better than the 4-legged one. So this is the 2-legged version, walking downhill. And I think this is Steve Collins, who was an undergraduate in my lab, is now a professor at Stanford. This robot was first built by Martijn Wiss, who was I referred to earlier as in my lab. So this is, I think, in terms of what passive dynamics is about, no one's made anyone better than this one. And at the time, and I think this was actually true until maybe 2 years ago, there was no robot with or without motors that looked more like a human walking than this one. Right, so all the big motorized, so it's like we succeeded in the Wright brothers crusade of making a glider, right? This glides down the ramp, and it works better than any of the other powered robots. Until actually, there now are videos of robots just in the past year or two that are maybe as natural looking as this one is. Okay, any questions about this robot? Now is my sound working? Yeah, I got the sound. The sound's working still. Great.
Awesome. So how
Yeah.
was the shape of the feet in front?
Okay, so because we wanted this to work in 2 dimensions, not 3 dimensions, you have to keep the center of pressure inside the foot, or the foot capsizes. So this actually walks sort of back and forth, left and right, and the feet, the bottom of them have little curves here, and these 2 curves are not the same as each other, and they're for the purpose of guiding the center of mass, sort of an S-shaped curve here. And then we say, well, we don't want the heel strike to be a big problem, so there's a soft, compliant heel. So even if it doesn't land just flat, it doesn't get a funny kick to the side. And actually, we read the patent for. Let's just see if I can find it here. We've got gliders, we got toys. We've got this thing. The patent for this toy here talked about the shape of this feet here, and it talks about that you have to shape them so the center of mass goes like in an S-shaped curve down the ramp. Okay, does that address your question?
The other question is we have a lot of flexibility at the hips, well, a lot, but okay, we have some flexibility at the hips, right? But these robots don't have flexibility at the hips, correct?
This robots do not have flexibility at the hips. That is correct. They only have 1 degree of freedom at the hips, which is a sagittal swing. They have no adduction like a sideways kick, and they have no twist about an axis. That's true for all the robots I showed you so far. That's true for all the robots I'm going to show you actually too. Okay. Is something that for 3D robots is something we talked about a lot, and I think that's not really essential for pretty much most of walking. Okay, so we've got this thing that works pretty well, and we say, okay, let's take an idea. So this is what's inspired Tab McGear to make his first downhill robot. Let's make robots that are like planes or toys that are powered by gravity. Let's make them work. And then we have, you're doing math and morphology, so I can use math words and impress you, make it look like this is not just toys. We calculate the dynamics of these things. It's hybrid dynamics with the non-holonomic constraints. And we do a numerical search for limit cycles, and we find fixed points, which give us limit cycles. Then we make a Poincare map, and we evaluate that numerically, and we get a matrix for that map, Jacobian, and then we look at the eigenvalues of that Jacobian and try to get them all inside the unit circle, and we tune the parameters until we get them inside the unit circle, and that's how we design those passive dynamic things. So there's math in there. The people who made those original toys didn't do that math, but we did that math for the McGear's robot, and so did he. Okay, then now they're energy effective because the cost of transport is the slope in terms of our way of working. And then if they were functioning going downhill, they should function when we add a motor the same way the Wright brothers were. Now, how does that go? Well, to do precise mechanics reasoning, we would have to put a jet engine in the center of mass of each link. But okay, we don't have to do it maybe that precisely. Maybe we just have to add a little bit of energy in the same way that if you want to take a multi-degree of freedom system and you want it to come to a stop, you just put a dash pot anywhere and it will damp out all degrees of freedom. So maybe we just need to add a motor kind of anywhere or kind of okay place. So that let us make this machine. So this is again Steve Collins. And he was going on to be a graduate student, but he set out to add motors to that design. And then he finished working on it when he was a grad student at Michigan. He came back. So take this design, this passive robot, and add a motor. Now, what we decided to do is add a motor in the most important place of the motor for walking, which is ankle extension. So we put a hinge here, and then we extended the ankle. We just wanted to put a little motor, but we needed a big push off, so we made a spring, and we cocked the spring and then set the trigger, and then we have to have a sensor when the foot hits the ground to kick this thing off. And it turns into a contraption. And the contraption looks like this. It's conceptually just the previous design with a push off, but there's lots of parts. How big a computer is in here? It's like a little $2 microprocessor. It's about 60 lines of code. It's not a neural net or model predictive control or anything like that. The sensing it has no gyroscopes. It has no IMU. The total sensing in here is a little switch, 50-cent switch that senses when this thing touches the ground. And then it runs its program. When this foot hits the ground, this foot pushes off. After this pushes off, then a motor winds up a spring and like that. And you'll be able to see it in action here in this video. And this was it's not quite as evocative of a human gait as the passive one. And the reason for that is that because we have to put all this hardware down here to make the springs and the catch and the release and so on, the moment of inertia of the leg is bigger and the characteristic swing time is longer, so it's a little sluggish. The other one has lighter feet, it's a little more lively. But nonetheless, it's still pretty evocative of human gait. And it's basically a passive dynamic robot with a little bit of a motor in it. So we made a big advertisement for this being a way to make robots, and I think that's I'd say we drank our own Kool-Aid, and a bunch of other people drank the Kool-Aid too. Okay, so then, do you have any questions um, about this robot or anything so far? Yes, please.
So how stable are these robots to perturbations? So
Yeah.
they'll move, and if you poke them in any given direction, how hard can you poke them?
Okay, just in case anybody else is wondering, I did not pay him ahead of time to ask that question. Okay. So these robots are like incredibly reliable, and they work every time I show the video. Okay, but I don't show every video. So most of the videos are more like this one, maybe a little more extreme. Okay. This is the first time I showed this video in public. Somebody said, "Do you have robot videos of it falling down?" And I had to look on my computer in front of everybody to search because I didn't remember where it was on my computer. I just remembered the name of the video. You can see, so I just searched for this. You can see the smoke coming out of it over here. The name of the video was, oh fuck. I did this search in front of everybody. Okay, so now I do the same embarrassment. I just say it. That's not spontaneous embarrassment. So we've got hours of the video of this robot falling down. And it's not very stable against perturbations. And in fact, not any of these robots are stable against perturbations. And the bicycle's not stable against perturbations. And all the toys I showed you are not stable against perturbations. So all of these things, we get this periodic motion. And it's stable technically, which means you put small perturbations in and the perturbations die out. But the basin of attraction is not very big. And I can we've done this like sort of technical calculations in this, and I'll show a slide coming up where we quantify this. Okay. So this was the thing. Everything was good. We were lying to ourselves and everybody else about that it was that every single one of these robots is fussy. This particular robot, we got in Science magazine and we got lots of publicity. And I thought, okay, great, they're going to have TV cameras. And Steve spent a month at Cornell and he couldn't make it walk again. He's never walked again after like these videos I show. These are not representative videos. These are all the videos of this thing walking. And then you take any of these robots, like this one, it's really delicate. Like it has good days and bad days. This one, not sorry. This one, if you're around it for a while, you can make it walk every time. So it's a little bit robust, but it's not super robust. You have to learn how to use it. This one, I've got another funny story about. This one also got some publicity. And so a bunch of people saw it and saw that it's like, the research budget for this is $10 for the Tinker Toy set that you can make this. And there was a bunch of 8th graders who set out to make this robot for their science project. So there's this girl who set out to make this, and it didn't work. And I said, did you try adjusting the slope? And then it didn't work. And then I just said, you try, playing with the weights here? It didn't work. And then I didn't hear from her for a while. So after a few months, I wrote back to her and I said, how'd it work? And she goes, fantastic. I got first prize in the science fair. And I said, first prize, but last time I talked to you, it didn't work at all. And she said, yeah, I never got it to work, but the judges were really impressed that I had an email correspondence with a real scientist. So I don't know, 5 or 10 people over the years have tried to make this, and like one has succeeded. It's incredibly fussy, right? or these toys. This one, it works, but it's typically it'll wander off to the side. You have to have just the right slope. It's not the kind of thing that most people have patience for. Like in the 50s and 40s, you could do this. You couldn't sell this toy really now because it's just sort of frustrating. And then this one, as I said, it barely works. So what's the problem with passive dynamics? This whole thing I tried to sell you, which we sold pretty well. We got this article in Science Magazine saying this is a great way to make robots. And we got a lot of publicity. So there's a lot of things wrong with it. So one thing, if you just go back to the beginning and look at what the Wright brothers did, I literally misunderstood the Wright brothers in terms of the inspiration of this thing. So the Wright brothers, what they said before this is 3 years before their powered flight, they said the flight of the buzzard is similar to sailors. Buzzard is a kind of bird, and by sailors, I mean the kind of birds that glide well, is a convincing demonstration of the value of skill and the partial needlessness of motors. So they were into the gliders, but they had a different idea about them. It's possible to fly without motors, but not without knowledge and skill. So these guys were bicycle mechanics. I don't think they knew that bicycles could balance themselves. They knew that you have a bicycle and you have to learn to balance it. And they thought about flight the same thing, that you have to learn how to balance the airplane. So when they built these gliders, they were not trying to make passively stable gliders that they were going to add motors to and get passively stable airplanes. They were trying to make airplanes that were unstable, like they thought bicycles were unstable. I think that's what they thought. And then learn how to control them. And then after they learned how to control them, they could add power and use my reasoning. But it wasn't like master gliding first, add power, and this passive dynamic sense of the control. It was master control first with a simpler system that we don't have to mess with all those cylinders and gasoline and stuff like that. And then once we've done that, then we'll worry about getting a reliable motor and propeller on it. Right? So they weren't trying to make it passively stable. And actually, their airplane was like explicitly not stable. So if you look at their airplane from the front, let's see if I've got this. I've got to aim it. Let's see. To make this not confusing to me, I got to put my picture up here at the top. Okay, to make this in the front, you look at this airplane, and I got to use me as a background, I guess. There's this tipping of airplane wings up, which is called the dihedral angle, and it makes the airplane kind of stable because it's like kind of sits in a bowl made by the wings. Their airplane has a negative dihedral. The wings are tipped. God, this is hard to see here. The wings are tipped down, so the airplane is naturally unstable like this, which I think was maybe their attempt to mimic the bicycles, which are sort of unstable like that. Or somebody said it's because it's for crosswinds. Whatever. They weren't trying to make a passively stable airplane. They were trying to make something that they learned how to control. And they're trying to master control, which in their case wasn't a robotics thing. It was trying to get their nerve systems to do it. Okay, and I don't think they thought about passive stability at all. Now there's more things about this.
I have to make a small comment here, which is that it's around noon. So I want you to ask if we won another lecture of yours anytime soon.
Okay, so let's see. So I have to end this lecture. I'm happy to just do part two.
Yes.
Part two would be shorter, quite a bit. I mean, it's maybe 10, 15 minutes is what I need. But apparently, if this is not the right time for it, we can do it another time, or I can go really fast and just talk for 5 minutes. Which would you prefer?
Well, to me, I have time. I don't know if the other members of the audience have extra time.
You're recording this, right?
Yes, correct.
You're recording.
Yes. Yeah.
Okay,
Well,
so
we
why
have
don't I
to ask you permission, right? But yes.
Okay, but so let's go another 15 minutes, and then people who have to go can watch the recording. How about that?
Okay, sure.
So I'll aim for 15 minutes here. Okay, so these passive robots barely balance, and then we add motors to them. We should get a powered robot that barely balances, right? We knew that they were fussy. We just kept hoping we could make them not fussy, but we never did. And even the bicycles are fussy, and all these passive dynamic things. There must be some theorem out there that passive dynamic things which balance just barely balance, because they're all like that. Another is like we think, humans are kind of stable, but so maybe humans are like skeletons that walk and you add motors, but that's not the order of the evolution. You know, we had really fancy nerve systems when we were worms and fish, you know, back millions of years ago. And, you know, our nerve system was ready for walking way before our skeleton was. Like, I think all mammals can walk on two legs, and it's not. I don't think it's a especially evolved thing. But so you take, you know, don't do this at home, but you take off two legs of a dog or a cat, and they walk still, right? You can see this on YouTube. And it can be the right legs or the left legs or the front legs or the back legs, whatever it is. You give them two legs, they can figure it out. Like the nerve system's there. So it's not right that we had to use the skeleton and then add a nerve system. We had the nerve system, and then the skeleton came in, you know, the upright skeleton later. Here's a kind of conceptual one: is you know, you measure these people walking, us, and we barely use our motors, and you think, oh, we're barely controlling. But actually, the amount of control and the amount of motor use are not really related to each other. So here's, again, it's like this background video is not really going to work for us. So this is a mop. Okay, so here's a mop. And I guess I hold it in front of me. And I hold it upright. So this mop is held upright over me. Now, if I've got it just upright, and you went and measured how much torque am I applying to hold this upright? Well, if I'm accurate about it, the amount of torque I'm applying is approximately 0. Now, how much control am I applying to hold this upright? It would fall down if I wasn't controlling it, right? So I have the better and stronger the control is, actually the less torque I have to apply. So measuring the torque I'm applying is not measuring in any way the amount of control I'm applying, because I'm applying just such a smart, good control that I don't apply torque, right? I measure it so well that when it gets off by 1/10 of a degree, I correct it, and I never let it get in this position over here where I have to apply a big torque. So measuring the muscle use is not at all a measure of the amount of control, right? Really good control system makes itself invisible. It finds the way to not apply any torque.
I have a question about the mop example.
Yeah, please.
The question is this one. So I have weak memory of a page on a book by Arnold, which explains that in an inverted pendulum, it gets stabilized by like some vertical oscillations at the bottom.
Yeah.
Right. So I'm wondering if it is one can apply some potentially useless without perturbation oscillators at key points so that they take care of perturbations.
Okay, so first of all, my whole life is inverted pendulum. So everything I see is inverted pendulum. A bicycle's inverted pendulum, a toy is inverted pendulum, the walking robots are inverted pendulum, people are inverted pendulum. Everything's inverted pendulum. So it's the right analogy. So how do you think about an inverted pendulum being balanced? Is more or less somehow you have to get the center of mass over the support point. And how do you do that? Well, you move the support point sideways appropriately, and that's what we do on a bicycle by steering, or walking by stepping, or you somehow push the mass sideways at the top, which you can do. You have a little bit of control authority for doing that. For example, when you swing your arms, it causes a sideways reaction at your feet, which moves the center mass sideways. And then there's this funny trick, which is this: if you shake the base up and down a lot fast, you can balance things. And there is this thought, people have had the thought that mechanism of the shaken inverted pendulum is applicable to walking. And it's not. It's a really cool example in mechanics. I love it. I've given, here, look, we're on the World Wide Web. Here we are on the World Wide Web, and the second hit on this one is me. Okay, so here's me. This is on the World Wide Web, and it's me explaining exactly the problem they were talking about. So let's see. Goes. Where is it?
Okay, it's mentioning that we only see your slides. We don't see your your web page, the web page. So maybe if you copy and paste the
You
web
don't?
page.
Just me. You don't see whenever when I've been showing you web pages, you haven't been seeing them.
Correct.
How come you didn't say anything at the beginning of the talk when I was showing you all the web pages?
I guess someone mentioned it probably on the
I
chat.
see.
So that's maybe
Oh man, I thought I was sharing my screen. I'm supposed to be
so
sharing my screen.
the simplest way to fix that is just to copy and paste in the chat the link to the web page.
You can look it up yourself. Do shaken inverted pendulum. Okay, so I was talking about all these robots before, and you didn't even see them. Okay, well, I hope you got the idea by my description. Uh, it says here share screen. It didn't say I wasn't sharing an application, but somehow it just doesn't show my web pages. You don't see any web page here. Is that correct?
And now we don't.
Even though I'm sharing the screen, what does it do? It blocks Chrome or something?
Maybe it's
Okay.
behind your. Maybe it's even behind your keynote. I don't know.
It's in front in my book. Hang on here. How about now? Now what do you see?
Now we see a white screen, complete white.
So somehow your app doesn't like my apps, even though I'm sharing screen. I'm not sharing an application. Okay, well you can look up shaken inverted pendulum and you see it happens, but that depends on a downwards acceleration much bigger than g in the shaking, and in walking you can't do that because you'd leave the ground. So the shaken inverted pendulum, if you take this thing and you shake it up and down, to make it balanced by this shaking, you have to pull down with acceleration bigger than g. There has to be tension there, which there just isn't in walking. You don't have that tension, so that mechanism actually can't be part of walking. Okay. So here's like some theory that gets at this point. Here's a simple model of walking, which is a point mass and two legs, and you either have this thing walk downhill and make it passive, or if you walk on a level ground and you give it an impulse every now and then, and you control the step length. The passive version of this, which we call the simplest walker, you can investigate the stability and the basin of attraction and so on. And if we can characterize the basin of attraction by the velocity at mid-stance and the size of the next step. So we have a certain velocity mid-stance, size of the next step, and then we let it go. And what happens is we have to let it go in this blue region, which is a little blue region here with these long fingers. If you let it go in that region, which is if you zoom in, it's actually got a fractal shape and all kinds of weird structure. If you start it in that region, then it will just keep walking. So the basin of attraction of the passive walker is this blue region. Now, if we allow ourselves to control where the foot hits the ground and how hard we push off, the basin of attraction is this green region. Okay, so the basin of attraction of like a reasonable controller is about 400 times as big as the basin of attraction of the passive walker. So the passive one is stable, but really barely, and you can see the barely by the basin of attraction. So you asked the question about how stable is it? Barely. How stable could it be if we added control? Is this green region. So it's kind of ridiculous to start with this thing. And it's even ridiculous to say, well, at least it's stable to start with. Who cares if it's stable or not? Like the difference between this and not being stable is like nothing as far as the controller is concerned. The only thing you need from the passive system is that it's not unstable so fast that the control system can't keep up with it. Okay, so like our next powered robot was much simpler, but we just wanted to get one that was really reliable and could walk a long distance. So this robot, it looks like it's based on passive dynamics, but it's not. So unlike that Steve Collins robot with 60 lines of code, the fuck robot, this one's got like 10,000 lines of code. And it doesn't have a $2 processor in it. It's got like a $20 processor. It's not running, the sensory feedback on the Collins walker was 1 bit per step. This one is collecting, it's got a gyroscope and it's got current sensors and voltage sensors, and it's got, it's collecting, 1,000 bytes not 1,000 bytes per second, like 10,000 bytes per second. The amount of data per unit time this is getting to work is bigger than the Collins robot by factors of 10,000 or something like that. So this is entirely powered, but it's powered in such a way that it's going to be energy efficient. So the actual idea, which I think is important, is energy optimization. And energy optimization has overlap with passive dynamics, but it's not the same as passive dynamics. So when this thing is energy optimized, the swing leg swings pretty naturally, but it's still controlled the whole time. It's just the control only kicks in to make the corrections. And so this thing, it walked 65 kilometers on a battery charge, by far the world's record for walking robots. Used like the whole robot used, I think it's 16 watts. It's not using a lot of energy. Okay, so the new idea is passive dynamics was like a proxy for optimization. Actually, it's not a good proxy for optimization. And it's really not. Like if you go back to this model and you look at how much energy it uses when it goes downhill, and you look at how much energy it uses when we control the push-off, it actually uses 1/4 as much energy when it's powered than when it's not powered. The passive robot uses 4 times as much energy as the powered one. It's gravitational energy, but it's energy nonetheless. So like being smart about where you apply the energy gives you energy efficiency, possible energy efficiencies, which you don't get if it's passive. So it's wrong to think of passive as optimized. And then how do you make then a controller which is optimized and so on? And this is now a big problem. This is the whole issue of robot control. It's where everybody's working on it and trying to figure out how to make it work with model predictive control and neural nets and machine learning and so on. And so the new thing is you have a machine, you figure out what it's capable of doing, and you try to figure out what is it that you want to optimize in the machine. And then in simulation, you try to optimize it. And then the problem is if you look at the space of controllers that you're trying to optimize over, it's so big that it's actually too big a computation problem. So the problem in control nowadays is posing an optimization problem that's tractable, that if you solve it, will give you a robot that's stable and energy efficient and so on. And so there are lots of ideas about how to do this, but if we just get down to hardware, we got a big grant from NSF to build this robot, which we want to control with using some kind of optimization and heuristics, because we can't really do the optimization of the full controller. It's just too big a control space. And this is, we think, a robot that we can make stable and we can make efficient, and would be like the world's most efficient humanoid robot that actually looks like a humanoid. Sort of one of the ideas of control is to think of it as the whole robot as a point mass and make a robust point mass controller, which we think we know how to do, and we think we know how to tell the robot how to act like a point mass. And then we'll get this thing to walk, except the problem is we need another $1 million, and we don't have it so far. So this project may or may not be over, depending on money we get or don't get in the next year. The engineer who's working on this has serious health problems, and so we're fighting lack of money and lack of human life. So that's the thing. That's basically the end of the talk. This is our target with our new optimization approach, and here's optimization with heuristics. And passive dynamics is a bad idea. And then even the robots, when people talk about our research, we've spent so much time on passive dynamics that when people look at this robot, they say this is an advertisement for passive dynamics. And actually, it's just totally not. We did no passive dynamic design of this at all. We have no idea if this is passively dynamic stable or not. It's designed to be motorized and controlled. Let's get it in sight here. Okay, so now I can say my talk's over and just we can do questions and then be done with it.
Okay, so thanks a lot for the great presentation. So we have many questions, but I think we can have some extra time for some other questions. Yes, Kelsey.
Cassie, Kelsey, you're mute. You got my problems. Now you know what it's like. Kelsey's trying to unmute. Okay. You unmute Kelsey. Oh, you can't unmute. Never mind. You can mime it. I understand what you are trying to say. No, I don't. Okay.
Questions.
Yes.
I'll one out. So with this particular robot,
This one or the fancy new one?
Exactly.
This
yes. This particular
this
one.
one.
Yeah, this
Yeah.
one, the one that made the epic marathon. So
Yeah.
you said it's making all these tiny sort of control adjustments, and it's making it a reasonable walking. It's like, how quick is the pace with which it has to make adjustments? Essentially, is it millisecond level, or is it sort of a couple of hundred milliseconds?
I have an answer for you. Okay, so you're right in the regime of all the stuff that I think about. So the thing is, how come you don't fall over, right? Because you're taking these steps, and the thing is, what can you do to affect the relative position of the mass and the support, right? You're just trying to keep the support under the mass. And you can say, oh, it all depends on all the moving parts and swinging legs and so on, but it actually doesn't. So your ability to affect your balance is actually all packed into two instances of time. So one is, where does the foot hit the ground next? And how the foot gets there doesn't matter. Now, when I say it doesn't matter, it's a quantitative statement. How much effect you have on the relative motion of the contact point and the center of mass between steps is you can move it on the order of a centimeter. But when you take a step, you can control the relative position on the order of a meter. Okay, so you say there's that one instant in time, which is where you put your foot. And then there's another instant in time, and this back foot, where the energy comes from is this back foot pushes off. You can watch it when it's walking. It just makes a quick little push off, and then it picks up so it can swing forward. How hard you push off affects how far the forward and backward motion. So these are things that happen more or less at an instant, once per step. How much you need to do, at the beginning of the step. So right now, this thing is about to take a step, and about half a second later, this foot's going to be up here. If you the robot, you've got an IMU here, you've got a computer, you know whether you're on track or not here already. So you have all of that time until that foot hits the next time. All this time to set that controller there. So the basic answer is you've got about half a second to think about what you've got to do and execute it. Now, if you say I've got a half second and then you wait till the last millisecond and your foot is off by 20 centimeters and you have to move it, in 1 millisecond, 20 centimeters, you can't do that. But basically, you can plan ahead. You can see whether you're on target to hit the foot. You have a long time. Now, in the most extreme, like we want to make a robust two-legged bipod. So we'd like to make it so that if somebody comes up and gives it a really solid shove, it doesn't fall over. So like you say, what do people do? And people can take a step in about a fifth of a second, 0.2, 0.3 seconds. So you need to have the motor power to take a step in about a fifth, about 0.2 or 0.3 seconds. And then you need the computer power to take the right step in that 0.2 or 0.3 seconds. But it doesn't have to be all that right, all right? It's just, it needs to be right enough to get you more balanced after one step than you were before, and then you can correct a step after that. Okay, so basically, the short answer is you have a long time.
Okay.
And this is like a thing that I say is domain knowledge that some of the people doing robotics, who come from a robotics background but don't think about inverted pendulum, don't know, is that you have if you have a robot that looks like this, and it has 12 degrees of freedom, and you're trying to control 12 degrees of freedom, and you've got encoders in your motor, and you're doing a control, say 100 times a second. So every second, you've got 1,000 numbers. You've got 12 times 100. So 1,000 numbers you got to spit out here. There's only 3 or 4 numbers that make a difference. And it's not, you can't pick it out as one of those 1,000 numbers. There's some synthesis. It's where does the foot hit the ground next, and how hard does the last foot push off? So the actual control space isn't 4,000 numbers per step. That's that giant optimization problem we can't do. It's 4,000 volts per step. Is where did your foot hit the ground, and how hard do you push off? And that's almost the whole control. People argue about it. They say, well, how come when you're falling over, you swing your arms? And it's because, swinging your arms can do about the equivalent of stepping an inch. If you're about to fall over, you don't want to fall down, and you want to get that extra inch, and that's why you swing your arms. It's not that it gives you that much. It's that when you're in a panic, you use everything you got. Okay, who asked the question, and did I answer it?
Yep. Fantastic.
Okay, good. Okay. Anybody else? I love questions and answers, favorite part of the talk.
Other questions then. So maybe I have a question about the stability or instability. So with respect to which perturbation are these robots less stable?
Well, I guess I don't have a good answer to that. So this robot that's on the screen now is a 3D robot. So it's going to have sideways perturbations and front and back perturbations. And my guess is that if you do it by basin of attraction, like what's the biggest disturbance it can take? Just the architecture of the thing is that it can take bigger steps front and back than it can side to side. So assuming that we get the control design working and we get the hardware working, it'll take bigger perturbations front and back than sideways. If you go back to this robot, which doesn't look all that different from this robot, it doesn't have a life sideways. It's only got a life front to back, and I can't really tell you what are the perturbations? You can perturb the leg, you can perturb the center mass. There's not much you can perturb, and I don't have a simple quantification. Like if we have a good controller, we can recover from all of these disturbances here. They're not dimensionally the same, so you can't even really compare them, which is bigger. They're big. That
picture with a very small, I don't know what to call it, very narrow basin of attraction. It's kind of common in all of these similar dynamical systems, right?
This is a small basin of attractions, you mean?
Right.
Yeah, they have these little. Actually, okay, that Arnold example you gave of the inverted pendulum, they have these little stability tongues and so on, right? The domain of attraction is these funny little regions, right? But when you add control, you get rid of all those funny regions.
Yeah, that maybe is an indication of the fact that the passive models they are lacking something a lot actually, because in practice we don't see this complicated stability when people walk other than if they have injuries or.
Yeah, it's really robust. I mean, the example I like, we have these robots and we're afraid of them falling down. Imagine standing and next to an American football player or even South American, whatever, either kind of football. You stand next to one of those people, you're not afraid that they're going to fall down. In fact, you try to knock them over and you can't, right? So you can certainly God could make a very robust controller. And we think we can too, because we've got sort of theoretically what we could do. It's like if we get strong enough motors and good enough sensors, we should be able to make a robot that basically you can't knock down, right? Unless you knock it so hard that if it takes a 1 meter step in a fifth of a second, that's not enough to catch itself, right? So we should be able to make a super robust, like a soccer player, like a football player robot, if we can implement a control like this, which means you have to take a full long step in a fifth of a second, Now this assumes you can take a full long step in a zillionth of a second, but we get most of it if we just can do it in a fifth of a second.
Awesome.
Okay.
Questions?
Come on, ask a bad question, somebody. Good question, bad question.
Any questions?
Come on, there's got to be a good question. There got to be a question.
Other questions? Okay. No?
Okay, let me ask one for you. Once I gave this talk and somebody said, all this passive stuff, I did this for like 20 years, right? And somebody says, oh, Andy, you shouldn't feel so bad. The whole thing about controls is you have to understand the plant. And now you understand the plant. So it's good. You didn't lose anything in terms of controls, like feeling bad for me that we were barking up the wrong tree all this time. And I just don't feel like that at all. Like, that's what it took for us to figure it out, right? It turns out that where we end up when it's all done is not that far from where everybody else is, except still I think there are things that I know, like this idea that in this control there's only like these key numbers. Where do you put your foot and how hard do you push off? Sounds simple, but most people don't know that. But I don't feel like, oh, damn, we spent 20 years on the wrong problem. It's the way we got to understand what's going on, and it's not we couldn't have skipped it really. That's what I think. Yeah, so if you think, I think some people sort of like this talk because it's like admitting to like we had this failure, but it's not even really failure. It's just like this was the route to where we got to where we are. The failure is not knowing how to raise the next $1 million to finish this thing. That's the failure, but it's not. The failure isn't in the research. I don't think.
Yeah.
And now I ask the next question for myself.
Anything else? All right.
Okay, that's the end. We say goodbye. Okay.
Yes.
So listen, hey, this thing about WebEx is no problem. So it was a problem. Like I couldn't control the sound, and this thing you couldn't see my videos because it's trying to be so smart. It doesn't want to show my web browser. That's no good.
So let me first thank you, okay, for the So let's thank Professor Ruina for the great presentation, for the extra time that you dedicated to us. So that's awesome. So thank you very much. And there was no problem at the end with WebEx.
What do you mean? You didn't see the Slinky walking on the treadmill?
But that we didn't practice.
You didn't see the Boston Dynamics robots. You didn't see all the fancy robots falling down.
That is not fair because we didn't try it before. I didn't know that there was the problem with you wanted to show the videos when we tried it, right? Otherwise, we would have fixed that.
It didn't occur to me that would happen. I couldn't have predicted that without an experiment. Okay. Yeah, I don't know. Does anybody ever show the web on their in the middle of the talk? How do they do it?
I think that one of the things that less people have is Keynote. I think that you had a lot of extra features there, and not many people use Keynote. So I think that's one of the things. But other than that, I think that's the only extra thing, because the fact that you have to restart WebEx, that happens always basically.
No, but like right now, you don't see. Do you see anything?
Just white.
Just white. I've got a whole thing to show you right in front of you.
Yeah, but try to. It's possible that you have your page open in one of the two monitors. Try to move the page that you have open in another monitor. I believe that if you move it to the other monitor, it might show up.
Okay. You see anything?
No.
No, it's not. So I selected the page. I didn't select the app. I said show my whole screen. And when I did the sharing, that's what I did anyhow.
Catherine, do you know what could be the issue there?
The only thing I can say is that I haven't had problems with this, and when I go to share content, I have choices on the left of like when I go in, when I click the share button, it gives me options,
Yeah.
right? And it allows
Yeah.
me to share an application or not.
Yeah. So
Um,
okay. So now when I look at it, it says you're sharing Keynote, which is the problem. But
exactly. So you
when I
need to be
first
sharing
selected the
the
share,
screen, not the app, because what it does is it just hides anything else other than
no,
the apps that it's sharing.
when I started, I did that, and now
Yeah, initially. I think initially when you were testing things out, that's what you were doing, but somehow it got switched or something. I don't know.
okay, let me just try right now. I stop share, and I'm going to start sharing again, and then I go screen two.
That is right,
And
because when you I believe that after you came back from
yeah,
when you
Yeah,
I
there you
click
go.
on now. Now do you see things?
yes,
Yeah,
Oh man! So do you want to see the videos you missed, or
yes, let's see the
sure.
videos.
okay? Now, now I'll show you what you missed. So here's the shaken inverted pendulum, and this is me. This is I was saying, like I went on the World Wide Web to find shaken inverted pendulum, and the second hit is me. Okay, so this is this pendulum going up and down and balancing. Okay. Here's the experiment without the close-ups. Come on, run the experiment, man. Okay, well that's what you saw. You saw the video of it.
That's exactly
There it
what I
is.
So,
Yeah,
so the reason for
but
which I asked,
I'm,
so the reason for which I ask about which type of perturbations what should be most worried about is that so these situations here. Maybe- so what I'm saying that did you try to have these oscillations in different directions, like not always in the vertical direction? Because I understand the problem that you're describing. It might
so
be that
you can run. Okay, so this what happened? What does this vertical shaking do? It effectively adds a spring that tries to center this thing. You take this whole apparatus and tip it at 30 degrees. This shaking tries to hold it at 30 degrees, but gravity disturbs it a little more than that. If you turn it upside down, it wants to point down. And if you rotate the whole machine, it tries to tip to the side a little bit. So it's not really telling you which, I mean, remember this thing just has 1 degree of freedom. So the only perturbations you can do are in state or velocity, right? And then you can't really say, well, I guess you can put assign a size to them kind of. This thing, you know, when you shake it like crazy, like with the acceleration, 10 times acceleration of gravity, it's pretty stable. So here it is without shaking. It's not stable in slow motion. Right.
yeah, got it.
Here it is. I don't know if that answers your question.
Yeah, so I think I understand why that doesn't work. I'm just trying to figure it out if there is a version of that which works. Because
No, I think there's no you know, okay, so yes, we have passive stabilization, but the nature of the passive stabilization isn't from shaking, it's from the dynamics doing the right thing. So like the bicycle, it's something about the dynamics makes it so when it's falling to the right, it steers right. These passive robots, um, something about let me show you about the dynamics is that when it's falling forwards, it takes a bigger step. Right now, you know exactly how or why I don't know, but it's you know it does its self-correcting actions. It's not about shaking or something like that. It's actually complex dynamics.
so there is another thing that I wanted to mention, and it's this
Yeah.
one. Like when we fall down, like one thing that we do is that we tighten the cord. In practice, we decide on which we do something like that. We just reduce some degrees of freedom and then do
Yeah.
something extreme. So
Yeah.
what I'm thinking here is like maybe one is to at certain point one is to block the hip movement or something like that, and then allow for some like some other perturbation, some other control. Because at the end, what I do when I fall, well, I tighten myself. Then I use some specific movement.
Okay, so that's a really good point. I've actually heard nobody make that point before, but I would say, you know, I said that we're underactuated, and the underactuation is that without stepping, we can't apply torques with our ankles. We can only apply small torques with our ankles because otherwise the foot capsizes. So but the rest of us is fully actuated. All the joints are actuated. The thing is, how can a system fail? It's like it's got all these degrees of freedom, but you have direct control over lots of them. So I think sort of the natural explanation for what you're saying is the essential uncontrolled degrees of freedom is the stuff that you have to manage with the push off and the steps. The whole other degrees of freedom, when there's a big disturbance, you have to manage those too. But the way you manage them is you go into position control and lock them. Right. So if you left your whole body floppy, then you might take the right step, but you know you'd be hanging sideways some crazy way. So, but you do have control over all those, direct control over how much your trunk is bent and where your arm is and so on. So I think it's a natural control approach to like freeze as much of your body as you can. And then the part that you can't freeze is the overall falling down, and that one you manage by taking a big step.
That's right. And what I'm thinking is that you just avoid like some nonsense things happening, that you can some chaotic motions of all the
Yeah, the whole body. So there's just, you know, in robot control, people like to think of the motors as torque sources. If you think of them as torque sources, then basically everything is floppy and everything has to be controlled in a sophisticated way. But if you just switch over to position control, then you don't have, you get rid of the control problem. And I think that's basically what you do.
Right.
That address here. So I think it's a good observation that I think is, I'm just in terms of the history of my thinking, I used to be in like passive dynamics but sort of another sort of associated world of thought is I used to like torque control, and I used to make fun of people who had position controlled robots. So now I think exactly the opposite, that really the effective way to make a robot is to put position control at all the joints. I'm still bucking that. I mean, it's not a common opinion. I feel pretty strongly about it, but I don't have sort of a mathematical justification for it. The closest to it is what I just said, which is that with torque control, you have to control all the degrees of freedom. With position control, you don't. You just lock them and you're done.
I think my main the most stupid observation I can make there is that at the end, falling down is when your center of mass is too close to the ground, and you see that so then the thing that you care about to not fall down is to prevent that. Now, whatever happens to everything else doesn't matter. So it's not that you fall down if your arm is close to the ground or something like that. So those things are inessential. For falling down, that thing is inessential. So if you have a way to just not make the center of mass go down, you're good. And that is a reduced amount of degrees of freedom. So you reduce all the degrees of freedom to the center of mass. That's it. End of the story. Then you control. Then you try to avoid that to go down.
I agree 100%. I agree with everything you said. But I can tell a joke. There's three of us now, but I can tell a joke now. Okay, you ready?
Yes.
The joke, it takes a whole minute to tell this joke.
Go.
There's a joke that I learned when I was in graduate school, and the purpose of this joke is like to make fun of people who are kind of mathematical. And the joke goes like this, and you probably know the joke, but I'll tell it. It's that the applied mathematician goes to the horse owner, and the horse owner is having trouble with the horse at the horse races, and said, "Can you study this?" And the mathematician says, "Yeah, I can do that." And the mathematician comes back 6 months later and said, "I've solved your problem." And the horse owner goes, "Yes, what's the solution?" And the applied mathematician goes, "Well, assume a spherical horse." Okay. Now, do you know that joke, right?
No.
You know that joke, right? You don't know that joke.
No.
Okay, well, you don't know, neither of you know that joke. Okay, well, so it's like making fun of people who are math people, like who oversimplify everything, right? And when I first told that joke, I used to tell it a lot. It's like making fun of like me, because I was sort of a mathy kind of person. Okay, well, little did I know that I was going to actually be somebody who studied horses, right? So I have papers on how horses get around and stuff like that. Now, if somebody came up to me and said, I've got a model of a summa spherical horse at this point in my life, I would say, why such a complicated model? Why not just a point mass horse? Right? I'm on the other side of that joke now. I'm completely on the other side of it. It's like point mass horse, that's all we need. And so because of what you said, it's like the essential problem of getting around is just managing the center of mass, right? And that's true. And it's true. We have a whole paper, is he well cited? It's a good paper about like, modeling a horse with a point mass. so, so it's like you said, that's like, it has the whole story in it.
Awesome. Oh yeah. So when are you coming back to North America?
I'm coming to Ithaca on December 12th, and I'll be there for a week or so, and then I'm going to San Francisco for a week or so, and then I might go back to Ithaca. I've got my business partner, my robot partner, is sick, as I said, and I'm going to go see if I can help him out.
Because you're closer if you are in North America, right, than if you are in India, right? It's complicated to make it from
India is far away.
Yeah, good. Well, I think we stole 2 hours of your time because you connected at 11. No, what was it, 10:45 to fix way back. So don't want to take advantage too much of your time. So
okay.
Thank you so much for
as far as the other things you can watch on the video is watch Slinky on a treadmill. You can look that up yourself.
Yes, I'll watch that. I'll watch that.
And watch the other one's called DARPA Grand Challenge Walking.
Yes. Yeah, absolutely.
Okay.
Well, thank you so much. Thank you so much. It was a great pleasure to have you here.
Okay. Thanks. Fun.
Bye-bye. Bye-bye.